Today we're going to take a look at section 2.2, which will be our discussion of Venn diagrams. First thing I want to show you is what a Venn diagram looks like. The basic look is that it is a rectangle, and inside of the rectangle you have one or more circular shaped objects. So we have like a circle or a square, or a circle or an oval or something like that, oval shaped item inside of there. And this outer rectangle is called the universal set, and we would designate that with a U. So U is our universal set. I'm just about out of room there. And then the circle on the inside actually has another name, and it'll be the name A or B or some other letter. And this would be any other set in the universal set. We talked last time a bit about sets, and now I want to talk about what a complement of a set is. So for any set A within the universal set U, the complement of A, which is written as A prime. So sometimes you'll hear me say A prime, other times you may hear me say the complement of A. This is all elements in U, the universal set, that are not in the set A. And I want to show you what that looks like because we talked about this notation last time. We were talking about set builder notation. And we can write this in set builder notation the following way. So we start with our curly brace, we draw our X, and we do that that line. We say that X is in the universal set, so X is in U, but X is not in the set A. And this would be the description of a complement in set notation. So we're going to have a chance to practice some of these. So if you'll take a look, this is the universal set that we're going to be working with, which is the integers or natural numbers from 1 to 10. And I want us to find the complement of each set. So remember, complement means all the items in the set that are in the universal set U up here, but they're not in this described set here. In other words, we want to just write down the things that are missing. So we have the number 5 that's missing. And if we keep going, it looks like 6 is also missing. I have 7, but 8 is missing, and so is 9. So this would be the complement of this set. In other words, if we called this first set A, this would be A complement. Now, the universal set, this is an interesting sort of strange example, but I want you to be aware of it. So it's in here. And remember, complement means all the elements that are in the universal set that are not in the set we're talking about. So if we want to talk about U complement, then basically what we're saying is I want to know all the elements that are in the set U that are not in the set U. And you quickly sort of find out that that would mean that you've taken everything in the universal set and then you've removed it as well. So what ends up happening is that you get the complement that's the empty set. Remember we talked about that last class period or 2 class periods ago. So you can write it as the 0 with the slash through it or the empty brackets. And so just as the empty set is the complement of U, so also the complement of the empty set would be U. They're each other's complements. Last time we talked about elements of a set, and now I want to talk about subsets of a set. So A is a subset of B, if every element of A is an element of B. And the notation for that looks like this. So this is written A. It looks kind of like a sideways C. You put a line underneath it as well. B. We can read this as A is a subset of B. Sometimes I'll also end up reading this as A is contained in B, because that's sort of a visual imagery of what this would look like. We saw set equality last time, and we're going to see set equality again here with a slightly altered definition, since we have some new notation basically. So A, let's say it this way. If A and B are sets, then A equals B if, here's the condition, A is contained in B, or A is a subset of B, and B is contained in or is a subset of A. And if you combine our definition of equality from last time with the definition of subsets above, that's actually what's creating this new definition. So in other words, everything in A has to be inside of B, and everything in B has to be inside of A, just like our original definition was. It's just that now we're phrasing it in terms of subsets. Now, a proper subset, this has the same sort of feel to it as the subsets. So set A is a proper subset of B, and that is written, it looks much like the subset notation, but you don't have the equal line on the bottom. In other words, here's why. It is a proper subset if A is a subset of B and A is not equal to B. And that's kind of why you see that bottom line underneath the C sort of shaped symbol removed, is that it can't be equal to. This is much like when we talk about inequalities and we say things like x is less than 7 and x is less than or equal to 7. There are numbers that work in both of them. For instance, 6. 6 is less than 7. 6 is also less than or equal to 7. But there is specifically one number that does not work in the first one. If my x is actually 7, this part's okay, right? That shouldn't say 7x, but 7 is less than or equal to 7. But you can't say the first one. 7 is not less than 7, strictly speaking. So this is kind of the same flavor to it as we had with inequalities. Let's explore this a little bit more and take a look. We're supposed to decide whether the proper subset, the subset, both or neither of these should go in each blank. So the first one that we're supposed to look at has the set BCD on the left and the set BCDF on the right. So the first question to ask yourself is, the BCD on the left, are those elements of the set on the right? And the answer is yes. What that's telling you then is that it is a subset. We do in fact know that it is a subset. So the first notation for sure that can be used is the subset notation. But the second question we have to ask ourselves is it also perhaps a proper subset? And remember, the additional consideration to be a proper subset means it's actually not equal to the second set. And you can see real quickly that it is not equal to the second set. The second set is bigger. So if we take a look at that, what that means is that we could also use the proper subset notation correctly in that blank. So we ask ourselves then, if I can use the first one, the subset notation, if I can use the proper subset notation, what do I write in the blank? And the answer is I write both. Both of those symbols can be used in this blank. Number 4 shows a set 91735 on the left and a set 13597 on the right. And if you rearrange these or double check to make sure, they are in fact the same set of numbers, the same exact numbers on the left and on the right. So we do know, in fact, that every element on the left is an element on the right, which means the subset notation that we mentioned before, right up here, can be used for sure. We ask ourselves then, are these two sets equal? And they actually are equal. What's that telling us is that we can't use the proper subset notation, because proper subsets are only for sets that are not also equal, but they're subsets. So the only symbol that we can put in this blank is going to be the subset symbol. All right, so on number 5, we have two different sets again. The sets have the same number of elements. We have 5 elements on the left and we have 5 elements on the right. However, on the left, we've got this notation right here that has a -1. And this -1, it's not here on the right-hand side. It's missing. So what that's telling you is that there is an item in the set on the left that is not inside of the set on the right. And that's exactly what our definition of subsets says can't happen. So what goes in the blank then is neither. The first set is not a subset of the second set because it has an extra number that the second set does not have matching in its set. Let me actually talk a little bit before I get into cardinality about creating subsets, because we've kind of talked about what a subset would look like or not look like, but I want to actually talk about how we would go about creating one of these subsets if we were given the set. So let's just do a quick and easy one right away. We're gonna do this set that's got the A, a B, and a C in it. So we're going to create all the possible subsets. So one possibility is that our subsets are sets that have a single element in them. So A, or a set that's got just a B, or a set that's just got a C. So these are all of our one element subsets. But we also have 2 element subsets. That is a subset that's got the elements A and B, a subset with the elements B and C, or a subset with the elements A and C. We also have the missing subset that's got 3 elements in it. This is the only one that is not a proper subset. And then our final subset is actually the empty set. Every element in the empty set is an element of the set ABC. Not very interesting because it's a set that has nothing in it, but it is technically a true statement. So if we count over here, you'll notice that we have 8 subsets. Now, this is not the process you would want to go through if I asked you, how many subsets are there if you have 10 elements? If you do that, you're going to be taking, considerable amount of time to list all the different subsets out before you can actually multiply and add and whatever to find out how many total subsets you have. So there's got to be a better way to do it. And there is, in fact, the number of subsets can actually be found pretty quickly. So if n of your set A, that is the cardinality of your set A, is the number n, then the number of subsets is 2 raised to the n power. And we can check that real quick if we go back to the previous slide and see that that actually worked over here. So if you take a look, our n is 3. There are 3 elements in that set. And if I take 2 raised to the 3 power, that will be the 8 subsets that I got before. Let's take a look at what happens when we have proper subsets. Well, proper subsets simply remove, let's have our set up first. They remove the one set that has everything in it. So looking back on our previous slide, they would remove that set because it is the set that's equal to the original set. So if we remove that set, how many proper subsets do we have? Well, there's 7. It's exactly 1 less. And in fact, we can write it that way. So our proper subsets is 2 to the n minus 1. All right, so we're going to actually take this and put this into practice. We have a set A here, and it's got A, B, C, D, and E, which means that the number of items in my set A, if we count them up, would be 5. So part A says it wants me to find the number of subsets. And the way that I do that is I take a 2 and I raise it to the power that I just found up here, which was a 5. And if I do that, I have 32 subsets. And then I can very quickly find the number of proper subsets by simply subtracting 1. So this will be 31 proper subsets. All right, last one for today is actually a set builder notation with verbal description inside. This says set B is the set of all x. So set B is the set of all x such that x is an odd integer between -9 and 4. So we could list those all out if it helps us to see them, and I'll do that right here quickly. So this would include -7, -5, -3, -1, 1, and I think 3, and I think we're done. So if you count these up, you end up finding out that n equals 6. So we need to find part A, the number of proper subsets, the number of subsets, which is 2 raised to the 6th power, and if you multiply that out, you'll get 64 subsets. And on part B, you have 1 less exactly, so it would be 63 proper subsets. You don't actually have to list out the numbers from -7 to 3 here, but you can if you would like. And that will conclude our discussion of Venn diagrams.